Right, so this is the recording after the fact, since I lost microphone last time. So we're going to calculate the pH of a 1 liter bufflish solution that is 0.50 molar in ammonia and 0.20 molar in ammonium chloride when 0.01 moles of solid sodium hydroxide is added. So we're working with a weak base here, and these are going to be the same as weak acids, but now we're working with Kb, and we'll also be calculating pOH if we use the Henderson-Hasselbalch equation. So the first thing we need to do here is notice that we've got 1.0 liters of solution, so that means we don't have to convert, or that our conversions at least are automatic for ammonia and ammonium chloride, because we need to convert these to moles to calculate the stoichiometric conversion of either the acid or the base into the other, depending on what's been added to the solution. So since we've added sodium hydroxide here, that's a strong base, it will neutralize some of the acid. So this is going to be the acid portion of our buffer. This is the base. So we'll be subtracting 0.010 moles from ammonium chloride and adding it to ammonia. This is going to be 1 molar ammonia and 0.21 molar ammonium, 19 molar ammonium chloride. And of course, even when I'm recording at home, I can't remember to grab a calculator first. All right, so we take this now, we plug it into the Henderson-Hasselbalch equation. Now remember, when we're doing this for weak bases, when we're doing this for a Kb, it's pOH plus the log. And then this is similarly, since now we're starting with the base plus water, it's going to give us OH minus plus HB. This is also reversed from the acid, weak acid buffer form of this, and it's acid over base. Because here the acid is our product and the base is our reactant. So this is 0.01 plus the log of the acid, 0.19 over 0.51. And these should again be in concentration units, not just moles. Although I suppose in the end, don't know why I wrote that. This is 4.75. So 4.75 plus the log 0.19 divided by 0.51. So pOH is equal to 4.32. So now our pH is just going to be 14 minus 4.32. 9.68. Just like that. So when we're looking at any buffer, the relative amounts of acid and base are one factor that influences the effectiveness of that buffer. So the buffer is going to be most effective when the concentration of acid and the conjugate base are equal. So if we compare two solutions that have this pKa of 5, we can calculate the percentage change in pH when 0.01 molar of sodium hydroxide is added to each. So here we've got these two different solutions, one where we've got equal amounts of acid and base, and this other one where we have more acid than we do of the weak base. Mochi, I'm gonna need you to not do this right now. Cat's trying to climb on top of my iPad. Yeah, stay there. Okay, so when we do this, our solution 1 here has a pH of 5, and so we're going to be taking and adding this hydroxide that's going to reduce our acid and increase our base, and so we can calculate the pH as the pKa, which is 5, plus the log of the base over the acid, so 0.110 over 0.090. So 5 plus 0.110 divided by 0.09. And our pH, oh, I forgot the log in there. Is now 5.087. So if we take 5.087 divided by 5, that gives us, well, and then multiplied by 100, that's going to be 101.7%. So we increased by 1.7%. For other solution over here, now we already have more acid than we do base. And again, when we add a strong base, we are taking away from our weak acid and adding to the base. pKa here is still the same, but because we're starting with more of that acid than base, our pH starts out lower. So 5.0 though is the pKa plus the log of 0.03 divided by 0.17. So I'll just do this math real quick. And of course this equals pH. Our pH after the addition of that base is going to be 4.247 is where I'll round it off. Now 4.247, we'll divide that by our starting pH. And then multiply that by, oh, I did the wrong one. So divided by 4.05. And then multiply that by 100 to give us a sort of percent. And this is going to be 104.9%. So here we've increased our new pH to almost 5% larger than our starting concentration, even though we added the same amount of strong base. Whereas when we have balanced quantities of acid and base in our weak or in our buffer, we only increase by 1.7%. So to be reasonably effective, the relative concentration of acid and conjugate base should not differ by more than a factor of 10. Right? So using this base to acid ratio, a ratio of 0.1 is going to be very small, a very small amount of base relative to acid, and then a ratio of 10 would be a large amount of base to acid. So this is like saying 0.1 of our base over 1. I guess I should write it. Let me write it this way. I've been using A minus HA, and on the other side, this is like saying 10, maybe 10 molar A minus over 1 HA. But it doesn't have to be those numbers. Anything that divides to give you 10 or 0.1, as long as you're inside of that, you can have a reasonably effective buffer. The other thing that matters is the absolute concentration of the acid and the conjugate base, right? So if you have more of the acid, then you're able to neutralize more base before it's used up. If you have more of the base, then you can neutralize more acid before you use it up. So starting with a high amount of both conjugate acid and conjugate base, or I should say weak acid and conjugate base in our buffer system is going to give us a more robust buffer, because if either of those gets used up, then we no longer have a buffer because we no longer have weak acid and weak base. So now we're looking at two different solutions. Again, with the pKa of 5, starting pHs here also are going to be 5 because we have equal amounts of acid and its conjugate base. The difference, though, is that we have 10 times as much conjugate acid and conjugate base as we do in solution 2. So this is going to look very similar. To practice writing out that Henderson-Hasselbalch equation. So this is going to be pH equals pKa plus the log. This is going to be 0.51 over 0.49. So 5 plus the log of 0.51, 0.51 divided by 0.49. That's going to give us 5.017. Let's just call it 17. So if we divide that by 5, which was our initial pH, and then multiply that by 100, and times 100 here is just to make it a percentage. So it's going to be 100.3%. So we only increased our concentration by 0.3%. Or we only, increased our pH by 0.3%. So same thing over here now. We've added the same amount of base, but we have smaller concentrations of both acid and its conjugate base. So our equation here will look fairly similar, where our pKa is still 5, but now we've changed the ratio, we've changed the total concentrations here. And so if these total concentrations get smaller, then for the same amount of change in base, you're going to get larger fluctuations or larger changes in the ratio between your acid and base. So we'll do 5 plus the log of 0.06 divided by 0.04, and that's going to give us a pH of 5.1176. So 5.176 divided by our initial pH of 5 times 100 means that we've actually increased here by 3.5%. All right, so, and actually if you take this out, it's 0.35. So we got 10 times as much change in pH when we had 10 times less, or 1/10 of the initial concentrations. So for these outermost points, right, we talked about before that last slide that a ratio of base to acid can be as low as 0.1, a ratio of 0.1 base to acid, or as high as 10 times the amount of base to acid. And we can actually use this and calculate a buffer range for our, an effective buffer range for our buffer, effective pH range for a buffer. And we could do that actually by just taking and really calculating for a generic acid or base. This first number doesn't really matter so much. I'm just going to use, let's just use 5 from the previous side. So 5 plus the log of, and this here is saying that base, the amount of base, is equal to 0.1 times the amount of acid. So if our base is 0.1, then our acid is 1. And if we calculate that, we'll get 5.00 plus plus a -1. So the effective pH range here is going to be negative, or 1 less than the pKa, right? This is pKa. And so the only thing that changing the ratio does is adjust us up or down from that pKa. Then we can calculate this again, but now the amount of base is 10 times that what we have of acid. We can throw in the same pKa here, plus the log of now 10 times what we have in acid, so 10 to 1, and that's going to be plus 1. So 5.00, we go the pH for that. So again, the pKa doesn't really matter here. That just sets sort of our middle point, and then our buffer will be effective as long as we stay within 1 pH above or below that pKa. And that is determined by the ratio of base to acid. All right, so just restated here, the effective range for a buffering system is 1 pH unit on either side of the pKa. So when you have to choose a buffer, and you're trying to choose a weak acid for that buffer, use this as a rule of thumb to guide your thinking. The other thing you can do is if you, let's say we have our pKa of 5, and we know that we have a solution and we're going to be adding a lot of base to it, we can actually start off our buffer solution sort of enriched in acid. So we'll start out with a higher concentration of acid, even though that diminishes the buffering capacity a little bit, since we know we're going to be adding extra base. That'll start us out on the lower side of the pH range, and so we'll be able to absorb more acid, or be able to absorb more of that base with the extra acid that we added. So pause here, take a second, and either figure out why this is the answer or make a decision. In this case, we're going to have a pH, we want to have a pH of 7.35. So if we have a 50 milliliter, not 50, 500 milliliter solution, and we're starting with 0.1 molar solution of the acid, what mass of the corresponding sodium salt do you need to make the buffer? Take a shot at this on your own. We do need to choose HClO, hypochlorous acid, because that's the only thing that has a buffer range even close to what we're looking for. And then we can actually use the Henderson-Hasselbalch equation to calculate the ratio of acid to base, or really just solve for the concentration of that base that we're going to need to add. So starting out, right, we want a pH of 7.35. And we know our pKa now is 7.54 for hypochlorous acid, plus the log of, and we have a 0.1 molar solution of the acid, so 0.10, that'll go there. And then our base, I'll just use B, is what we need to solve for. So we can start out by taking the 7.35 and subtracting 7.54. And that is going to be 0.19, or negative 0.19, equals the log of the base over the acid. And now we can take everything and raise it to the 10, and that will mean, that will give us 10 raised to the negative 0.19, and that's 6.4. I'll go 6.45. I'm going to keep the whole number in my calculator. Sorry, not 6.45. 0.645. I'm keeping the whole number in my calculator. You should too. Equals base over 0.10. And then so 6.45. Oh no, sorry, the other way. 0.645 times 0.1 is going to be 0.0645 molar, and that's the concentration of the base that we need. So now that we have molarity, remember molarity is moles over liters. So moles over 1 liter. So if I multiply this by 0.5 liters, it's just taking 500 milliliters, converting it to liters. That's going to give us, we need 0.323 moles of ClO minus. Okay, so now we have the number of moles of hypochlorite, but we're not just adding hypochlorite, we're adding the sodium salt of hypochlorite. So this is going to be sodium, chlorine, I was going to write 16, but it's oxygen, and this is 22.99, 35.45, and 16.00. So now we're 0.323. I think I missed a 0 there. Sorry, this is 0.0323. Yes, okay. So 0.0323 moles of sodium hypochlorite times the molar mass, so 22.99. Let's go calculator, 22.99 plus 35.45 plus 16. That's 74.44 grams of sodium hypochlorite per 1 mole of sodium hypochlorite times 0.0323. That gives us 2.4 grams NaClO. All right. So buffer capacity, kind of what we've been discussing now, is the amount of acid or base that you can add to a buffer without causing a large change in pH. We can increase that with increasing the absolute concentrations or by making the relative concentrations more similar to each other. And then if you know that you need to neutralize primarily acid or base, then you can overweight the buffer in one of the components. So by either adding extra of the base or extra of the acid. So what's going to destroy our buffer? Should pause here, take a second, try and figure this out. But the thing that's going to destroy our buffer is anything that removes all of our, or consumes all of one of our buffer components, so either the acid or the base. And in this case, it's going to be A, because adding all of this strong acid is going to neutralize our weak base completely. Okay, and that's where we left off. So I will see you next class period.